Welcome back to the video lecture series of Digital Fundamental. Today we will discuss simplification of logic function using QMap. So let's start. What is QMap? This simplification of logic function using KMap is a quite easy procedure, right? Simplification of logic function using KMap is quite a simple procedure and convenient procedure. But this KMap is very useful up to the variable 4. Okay, this KMap is a very simple method up to the variable 4 when we have a large number of variables. So this KMap method becomes complex. Okay, this KMap method become complex after the 4 variables. Okay, and for a large number of variables, this KMap is not as convenient. So for the case where we have a large number of variables, this KMap becomes quite complex. Okay, so we have a method that is Quine McCluskey method. Okay, this Quine McCluskey Map method is very useful for a large number of variables, and this method produced a tabular form method. Okay, this QMap is basically a tabular method based on the concept of PrimeImplicants. This QMap method is basically used for a large number of variables and it is convenient. Okay, it is convenient for a large number of variables. So this QMap is a mapping method in which we can represent our logical functions in a tabular form, and then this can be simplified by considering prime implicants. What is prime implicants? This prime implicants is a terms which can't be further reduced. Okay, this prime implicant terms are basically a sum term or product terms, and these terms cannot be further reduced in a logical function. So these terms are basically known as prime implicants. This QMap method is basically reduced a sum of product term or says product of sum term efficiently by considering this prime implicant terms. This QMap method is basically works on a prime implicants form. Okay, so here we can simplify the logical functions by considering these prime implicants, and we have our terms in a SOP form or in a POS form. Here we have a step-by-step procedure. This QMap is basically step-by-step procedure and it guaranteed to achieve simplified logical functions. So here we have a procedure to simplify the logical functions using QMap. So to simplify the logical functions using QMap, first calculate prime implicants. Okay, first step 1 is calculate prime implicants and step 2 calculate essential prime implicants. So in a QMap, first we have to calculate prime implicant, then calculate essential prime implicants. So how we can calculate prime implicants and how we can calculate essential prime implicants? So let's check out. So here first we have a calculations of prime implicants. This calculation of prime implicants, so to calculate prime implicants we have to follow a step. So step number 1, arrange the logical functions. Okay, we have a logical functions in a number form. So here this logical functions, so we have to form a logical function in a form of ascending order. Okay, so here we have to arrange logical functions mean term in a ascending form in terms of number of ones. Okay, according to number of ones present in a mean terms. For example, we have a mean terms 0, 1, 2, 3, 4, 5 and so on. Okay, so in a 0 we have a 0 times 0, so 0 must be 1. Then in a 1 we have a number of ones 1 time. Then in a 2 we have a number of ones 1 time. Then in a 8 we have a number of ones 1 time. Okay, So we have to make a group and we have to arrange this min terms according to number of ones present in their binary representations. Okay, so we have to make a group and write that groups in a ascending orders according to number of ones. Okay, according to number of ones, make a group and arrange them in a ascending order. Then step 2, calculate or says combine those successive group terms. Okay, we have to compare the successive group terms and then combine them in which the mean terms are differ by only one bit. Okay, the mean terms are differ by only one bit. We have to combine that terms, and whenever we have this one bit difference, so we have to put dash over here. Okay, and remaining bits are same. For example, if we compare 4 bit, so it is necessary that in both the terms these 3 bits are equal and 1 bits are differ. So whenever 1 bits are differ, we have to put dash over there. Okay, so step number 2, compare and combine the terms which are differ by only 1 bits. And step number 3, repeat this step 2 procedure until we get the prime implicant terms. That means the terms which are not further simplified. Okay, so this is how we can calculate prime implicants. Let's discuss these steps with example. So here we have one example that simplify the logical functions, or says obtain prime implicants for given logical function f of summation of 0, 1, 2, 3, 5, 7, 8, 12, 13, 15. Okay, so for this given example, we have to just simplify or says obtain prime implicant. So how we can obtain that? So step number 1, we have to make a group according to number of ones present. Okay, so here we have a number of ones representations and then stable. Okay, here we have this logical functions that is in terms of a, b, c, d. So here we write a, b, c, d, and as we have a 4 variable, so we have to represent all the min terms with the 4 bit of binary. Okay, so here we represent 0 with like 0, 0, 0, 0. So first variable is for a, b, c, d. Then here we have a 1, so 1 is written like 0, 0, 0, 1. So 0 is a one group, so here we mark a line. Then here we have a 1, 2, 8, that is in a second group with number of ones one time. Okay, in this binary presentation number of ones are one time, so here we write 1, 2, 8. Okay, then here next group in which number of ones 2 times, number of ones 2 times, so here we write a group with number of ones 2 times. So here in this we have a 3, 5, 10, 12. Okay, here we have a binary representation in which number of ones are 2 times. Then next number of ones 3 times. So in a 7 and in a 13 we have a number of ones 3 times. Then at last number of ones are 4 times in a 15. So here we mark a group. Okay, and write this group in a ascending order by considering number of ones 0 time, 1 time, 2 time and 3 time. Okay, we make a group like this. Now we have to compare successive groups. That means we have to compare this group of number of ones 0 time and the group of number of ones 1 time. That means we have to compare 0, 1, 0, 2, 0, 8, in which we have to combine the terms which are differ by only 1 bit. Okay, we have to combine the terms which are differ by only 1 bit. So here we have this 0 and 1. So in a 0 and 1, if we check, so first in a 0 we have a 0, 0, 0, 0, and in a 1 we have a 0, 0, 0, 1. That means 3 bits are same and 1 bits are different. So we can combine this term like 0, 1, and we can write like this 0, 0, 0 dash. Okay, because we have a 1 bit difference only that. So 0, 0, 0 dash. Same here we can compare 0 and 2. In a 0 and 2 also there is a difference of 1 bit. Remember, we have to combine the terms which are differ by 1 bit only. That means only 1 bit difference. If 2 bits are different, then we cannot combine that terms. Okay, so by considering that concept, we can make a second table like this. Okay, so here we combine the group terms. So that means the terms over here are combined or simplified in this form. Okay, so 01 is combined, 02 is combined, then 08 is combined. Okay, so this is how we can simplify our logical functions with step-by-step procedure. After one comparison is over, we can compare next successive groups and mark a line over here. Okay, so here we compare the groups and write all the combinations over here which are differ by only one bit. Okay, which are differ by only one bit, so we can write like this, and we have to mark the conditions, we have to mark the values which are used over here. Okay, that means if this table A and here we have a table B, so all the terms of table A are combined in a table B, so we have to mark that table numbers. Okay, so here we check out the values. So here that 0 and 1 is used, so 01 is checked out, then here we have a 02 is used, so 0 is already checked out, 2 is check the 2, and then check all the entries. So it means here all the terms are checked, that means all the main terms or all the terms are basically simplified over here. Okay, so all the terms are simplified over here. If any terms remain unchecked, that means it is prime implicants, that means this term is not simplified over here, so we have to write the logical functions of that. Okay, because we write logical functions of prime implicant, so we have to check out how many terms are simplified over here. So all the values are here simplified. Okay, now we have to again compare, we have to repeat the procedure and we have to make a next table. So we have to again compare this successive group table, so we have to check out this compare the tables, and we have to check out the entries in which all the bits are same, only one bits are differ. Okay, so here we have a next table, so here we can first compare 0 1 2 3. So here 0 1 2 3, if we compare, so all bits are equal, only one bits are changed. Dash is also match. Okay, it is necessary to match dash position, then check out remaining bits. If all the remaining bits are same and one bit are differ, that means we can combine that numbers over here. So here 0 1 2 3 is written like this. Okay, 0 1 2 3 is basically written like this, dash 0 dash 0. Okay, 0 1 2 3 is written like this, 0 0 dash dash, because this both the values 0 0. In 0 1 we have a 0 0 0 dash, and in a 2 3 we have a terms that is 0 0 1 dash. Okay, so we can combine that term and write like this, 0 0 dash dash, because two bits are equal, one bits are different, and there is a dash also. Okay, so we can combine the terms. We have to first match the dash position and then check remaining three bits. If two bits are equal and one bits are differ, so we can combine that term. So we can write like this, and after this comparison of successive group, we can make a table number 3, and we have to mark numbers which are simplified over here. So here we mark all the entries. Okay, 0 1 used, 2 3 used, and so on. Here only two terms are unchecked, that is 8 12 and 12 13. That means these terms are not reduced over here. If we again compare this table C, so here we can't again simplify the terms. Okay, we can't combine the terms. So here we have a prime implicants. In a table C, we have a repeated terms, right? Here we have a 0 0 dash dash 0 0 dash dash 2 times. That means whenever we simplified the logical functions with Q map correctly, so we have in a third table terms which are occurred twicely. Okay, that means here we consider all the terms. If we have this terms twicely, it means we simplify the logical functions in a correct manner. Okay, so here we make this table C. Okay, in table C all terms are occurred twicely. Okay, but in a logical functions we can write only one terms. Okay, so here we have this prime implicants terms and this remaining 8, 12 and 12, 30, which is also prime implicant. So here we can make a remaining terms, okay, and we write table like this. Okay, so this all terms are our prime implicants, and related to that terms we have a combinations over here. Okay, for 0, 1, 2, 3 we have a 0, 0, dash, dash. So we can write logical functions for that. Here C and D is dash, dash, and for A is equals to 0, B is equals to 0. Here we can write logical function like A dash, B dash. Okay, because A is equals to 0, B is equals to 0, so we can write logical function like A dash, B dash, and so on. Using this concept we can write all the logical functions over here for each and every prime implicant. So here we have all these terms are prime implicants. We can write our logical functions like this. But this prime implicants is not always a simplified version of our logical functions. Okay, it may possible that we have some other terms also included in this prime implicants. This is not a minimal solution. Okay, this is not a minimal solution of our logical functions. To find out minimal solutions we have to calculate essential prime implicants. Okay, so these all are the prime implicants. This is how we can calculate prime implicants. Now how we can calculate essential prime implicants? So here we have a calculation of essential prime implicant. This essential prime implicants are terms which are always present in a logical functions. Okay, essential prime implicants are terms which occurs always in our minimal expression of logical functions. This essential prime implicant is basically calculated by making a prime implication chart. Okay, by making prime implicant chart we have to identify the prime implicant terms in which if we make a prime implicant chart, so in that prime implicant chart if we have this prime implicants in which in only one row we have a cross. Okay, so using this we can identify our essential prime implicants. So this essential prime implicants is basically a prime implicants in which this values or says logical functions are always present in a minimal solution. Okay, these prime implicants terms are not always present in a terms. Okay, but these essential prime implicants are always present in our minimal solutions. This essential prime implicants is calculated from prime implicant charts, and using this essential prime implicant it is necessary that all the terms are covered in a essential prime implicants. Okay, all the terms should be covered in a essential prime implicants. So essential prime implicants are our simplified logical functions. Okay, if we identify essential prime implicants and all the terms are covered by that essential prime implicant, so we have our minimal solutions. But if all the terms are not covered by essential prime implicants, so we have to also cover that prime implicants also in our minimal solution. So how we can calculate essential prime implicants and how we simplified our logical functions. Okay, so let's discuss with previous example. In previous example we calculate prime implicants. Now let's calculate essential prime implicants. So here we write our example and prime implicants. Okay, by considering this and making a map like this, we can calculate essential prime implicants. Okay, here we marks the entries 0, 1, 2, 3, that is our prime implicants combinations, and regarding that our terms, that is A dash, B dash. Okay, so here in this we write all the terms like this 0, 1, 2, 3, 5, 7, 8, 10, 12, 13, 15. So all the terms are right in this way. Okay, and all the prime implicants are written like this 0, 1, 2, 3 combinations, and all the combinations are written like this 8, 12 and 12, 30s. Okay, we can write like this. Now we mark a line like this and mark line like this, and mark a cross over the terms which are used, because as in this 0 1 2 3, okay, 0 1 2 3, so mark a cross at a 0 1 2 3 and so on. Okay, so for all the prime implicants, mark all the entries, mark cross for the terms which are included with given prime implicant. That means 0 1 2 3 is basically cover this 0 1 2 3 term, then remaining prime implicants covers all these terms. Okay, so we mark a cross over here, so this is our prime implicants. Okay, now how we identify essential prime implicants? So check out the row wise. Okay, so at a 0 we have a 2 time cross, then at a 1 we have a 2 time cross and so on. So if we compare this column wise, okay, if we compare the column wise, all the entries have a 2 time cross, but the entries in a 10, at a mean term of 10 we have a only 1 time cross. Okay, in a 10 we have a only 1 time cross, and in a 15 we have a only 1 time cross. Okay, so in a 10 and 15 we have a 1 time cross. So for a 10, which terms are basically, so for a 10 here we have a entries, that is b dash d dash. Okay, for this 10, if you check out the values, so this 10 is covered by the mean terms b dash d dash. This 15 mean term is covered with b and d. Okay, so this b dash d dash and bd is our essential prime implicant. That means this b dash d dash and bd must be in our final minimal solutions. Okay, now this b dash d dash and bd must be covered all the mean terms. Okay, b dash d dash and bd must be covered all the mean terms. How we can calculate our essential prime implicant? So check out the row wise. Okay, if we have a terms which having only 1 time cross, there, so respective that we have our mean terms which is our essential prime implicant. So here at a 10 we have a 1 time cross, so regarding that we have a b dash d dash, and at a 15 we have a 1 time cross, so for this we have a term that is bd. Okay, so we have a b dash d dash and bd is our essential prime implicants. Now we have our final expression, that is b dash d dash plus bd, but this must be cover all the terms. So let's check out that b dash d dash and bd cover all the terms. So how we can identify? So this b dash d dash has a combinations, that is 0 to 8 10. So we have to mark check out over here 0 to 8 10, and then this bd has a combination which is 5 7 13 15. So we mark check out over here. Okay, so all the entries are covered, but this 1, okay, this 1 and 12, okay, this 1 and 12 is not check out. That means using this essential prime implicant, this 1 and 12 is not covered. Okay, this 1 and 12 is not covered, so we have to again consider the terms which are covered 1 and 12. Okay, so for 1 we have a 2 cross, so for a 1 to write expression for 1 we can write any of the terms. Okay, and for 12 also we have a 2 times cross, that means respective terms we can write any of them. Okay, so to consider a 1 we can write values of a dash b dash or a dash d. We can consider 1 by considering either a dash d dash or by considering a dash d, and again to cover this 12 we can consider any of the terms a c dash d dash, okay, or a b c dash. So by considering any of the terms we can cover 12. So this is how we can write our final minimal expression, that is our essential prime implicants b dash d dash plus bd always present in a final minimal solutions, and we can write either a dash b dash, or we can write a dash d, or we can write a c dash d dash or a b d dash. Okay, so by considering any of the terms we have a 4 possible minimal expressions. Okay, so this is how we can simplify our logical functions by calculating prime implicants and by calculating essential prime implicants. Thank you.